My guest today is Professor Ryan Ogliore, who is Assistant Professor of Physics at Washington University in St. Louis. His research group uses microanalytical techniques to study extraterrestrial materials in order to better understand the formation and evolution of our solar system, as well as other stars. Welcome, Ryan.
Thank you. Thanks for having me.
Yeah, so I have a few of your papers that you had sent me, Ryan, but before we get to them, I want to set the context for, you study a lot on materials arriving on Earth or arrived on Earth. I understand that the solar system, probably 5 billion years old, Earth itself, 4.5 billion years old, perhaps. And then we have had heavy bombardment for a long period of time. All type of stuff came in. And so could you talk a little bit about sort of the historical context, how materials arrived and where they came from and what we know about them so far?
Yeah, so the meteorites, the natural materials, these rocks from space that we get most of our understanding from, the meteorites, really are leftover pieces of different asteroids and planets. We have pieces of Mars and the moon that also bombard us from space. And these meteorites, we have 66,000 of them, are a record of the various planet formation processes that started, like you said, 4.5 billion. We know this exactly. This is one of the benefits of our field, is that we have these laboratory techniques that are extremely precise. So the solar system formed 4.567 billion years ago. We know that precisely, and we call time zero the formation of the first rocks in the solar system. So we know that very well. The solar system's history, kind of prehistory before that, is from a molecular cloud, the type of molecular clouds that you might see in the Orion Nebula, if anybody does any backyard astronomy. So our solar system started by in a cold, dense molecular cloud like that. A piece of that cloud collapsed, and because it was spinning slightly, and this is a physics concept, and it collapsed to a very small fraction of that size, it conserved that angular momentum, just like an ice skater does when she does a twirl, a jump and spin. So that caused that material to spin out, form kind of a pancake, a flat pancake, and that's what we call the solar nebula. And at that point, it was a bunch of gas and dust, not a lot of complexity. And then my field, cosmochemistry and meteoritics, seeks to understand how we went from that really simple astrophysical cloud of gas and dust to the planets that we see now. So there are all kinds of chemical and impact processes that led us to where we are now.
Yeah, I would imagine it's a sort of a nonlinear process. So some parts of that cloud sort of condenses into something, and once it gets some sort of critical mass, I would think it start to attract other stuff, and then it grows bigger and bigger, right? So ultimately we have, well, we thought we had 9 planets before, now we have 8 planets, all formed through that process. But then there are a lot of small pieces that are out there, right? So I know about the Oort Cloud. So where exactly is the Oort Cloud in the solar system?
The Oort Cloud. So the Oort Cloud is really the furthest extent of the solar system. It's kind of the end of the solar system. 10,000 to 100,000 astronomical units away, where that's the orbital radius of the Earth. So this is this distant spherical cloud of comets. It hasn't been observed directly, but we have inferred its existence from the orbits of long period comets. And these comets are interesting, like Hale-Bopp was an Oort Cloud comet. But if you look at the dynamics of the solar system, it's likely that those comets were kicked out to those high orbits, those faraway orbits by nearby close interactions with Jupiter and Saturn. So somebody like me wants to study the most primitive material possible. And for that, we actually look at the Jupiter family comets. Those actually formed in the scattered disk beyond the orbit of Neptune, and those are likely to be the most pristine kind of time capsules of the formation of the solar system.
So is that what we call the Kuiper belt, or that's something different?
That's right. Yeah, yeah. So there's comets in the Kuiper Belt. The largest object in the Kuiper Belt is Pluto, like you alluded to. It's no longer considered a planet technically, but planetary scientists and meteoriticists don't really make that distinction to us. Like the moon is a planet. It doesn't really matter. And in that we mean it has a geologic history. It's an environment in and of itself. So we don't really make that distinction too much. You know, the larger the body, it has different types of geological processes happening. But yeah, so a lot of these bodies that I'm interested in studying spent the vast majority of their lifetimes in the Kuiper Belt. So they were cold and they were unchanged since their formation 4.5 billion years ago.
Okay. And I guess early on in the Earth's progression, we would have had a lot of visitors, so to speak, from the Kuiper Belt. But now it's sort of thinned out, right? There is many fewer members there, so to speak.
Yeah, fewer impacts now than there were in the first 10, 100 million years of the solar system's history. Basically, when the planets, especially Jupiter and Saturn, got into stable orbits, less stuff was flying around to bombard us. So we still get some visitors, thankfully, and that's how we understand basically the formation of the solar system through those meteorites.
So I want to go into your paper. So you have a paper from 2012, Incorporation of a late-forming chondrule into Comet Wild 2. You say the report a petrology, oxygen isotopic composition, and aluminum magnesium isotope systematics of a chondrule fragment from the Jupiter family comet Wild 2 returned to Earth by NASA's Stardust mission. So you talked about, you mentioned sort of the Jupiter family comets. Would you talk a bit about what NASA's Stardust mission is?
Yeah. So like I said, those Jupiter family comets were time capsules to the formation in the prehistory of the solar system. So the problem with cometary material is that it is incredibly fragile. And we know that by looking at cometary meteor showers that we know come from actual comets, and we can calculate the ram pressure at which those things break apart. So we know they're extremely fragile. They have the crushing strength of soft snow. So if you go to a really cold place and with freshly fallen snow, you know how fragile that is, and that's cometary material. So when we look at the meteorites, the stuff that makes it to the ground, the atmosphere essentially works as a filter to give us the most strong material, the most lithified rock, and that's not comet dust. So we don't have very much comet dust that makes it to Earth. But it's so important because it is that time capsule. So with that in mind, NASA sent a mission to a comet, Comet 2, and collected material. It didn't do it slowly. It collected it at about 6 kilometers a second into aerogel, which is a very low density foam that's not much heavier than air. So that served to somewhat gently slow down these cometary rocks that were collected when the Stardust spacecraft flew through the coma of Cometville 2 and returned those samples to Earth about 15 years ago now, actually. So, and these samples, so like I said, they're thought to be a time capsule of the solar system's very formation and prehistory. So it was called Stardust because we thought the material that was going to be returned from that mission was going to be that stardust that we're all created from. I think most people have heard that saying, like, we're all made of stardust, and we are. So this mission was seeking to go out and find that stardust. And what that is very isotopically anomalous. So these are very simple minerals, but their isotopic composition is very exotic, very small grained, material that we see in astronomical observations when we look out into the interstellar medium. So we thought that material, that mission was going to return material like that. And like all great like NASA missions and these kind of big projects, the exact opposite happened. So we went and brought it back, and when we developed the very difficult techniques to analyze these very small rock fragments that are too small to see with the naked eye, we found that a lot of them were igneous rocks. So the types of igneous rocks that we might see in asteroids, and not that really, really fine-grained, exotic, but yet simple mineral stardust that we were looking for. So this paper that you mentioned, that a group of us, it was a whole consortium, worked on, to me is like the canonical rock from Comet Wilt 2. It's an igneous rock. It appeared to have formed quite late in the solar system's history, and it bears some resemblance to the types of rocks that we see in asteroids that we're bringing back now. There's a current mission bringing back asteroid dust now, so I expect it to look somewhat like this rock iris that we studied in that paper.
So what's the explanation for that, Ryan? What are these things sort of went round trip, so to speak, came in and then picked up some materials and went back? What's the explanation for it?
Yeah, so I sent you this paper because we're writing another paper right now that this has confused me and the community since we published this almost 10 years ago now. So there's a lot of debate when this came out. So what happens in protoplanetary disk, like the solar system's infant disk, is that and we see this now when we look at protoplanetary disks around other stars, that immediately you start accreting material and you start forming planets. And when you do that, you carve out a gap in the protoplanetary disk. And we see this with this ALMA telescope in Chile now. We see these spectacular images of these disks with these big gaps in them. And in our solar system, it's thought that Jupiter carved out that gap. And if you have a gap there, you can't move stuff from the inner solar system to the outer solar system where the comets formed. So this rock, which appeared to be an igneous object that formed in the inner solar system, ended up in the outer solar system. And at the time, I assumed that this happened before Jupiter formed. But in the 10 years since then, there's been a whole lot of work in my field to analyze all these different types of meteorites. And it was found that the meteorites are split bimodally into two groups, inner solar system and outer solar system. And that combined with dating shows that Jupiter likely, the rocky core of Jupiter, likely formed very, very quickly within 500,000 years. And so this object, Iris, from the comet formed more than 3 million years after the start of the solar system. So lately, some of my colleagues thought, well, maybe it formed outside of Jupiter. There is some exotic process colliding planets outside of Jupiter that heated rock up enough to melt it and form an igneous rock like this rock Iris. So that's what we're thinking now, and we're doing some more analyses to test that hypothesis.
Yeah, I mean, Jupiter is a big player, so to speak, in the solar system, right? Mm-hmm. It almost acts as a vacuum cleaner in many ways. And so could it have cooked up some things and put it out there? Is it sort of a factory of creating materials? And
yeah, I think there's an idea that bow shocks from forming planets could have processed material to the igneous rocks that we see now. So yeah, possibly proto-Jupiter and other planets that have since died and we only have fragments of them left, could have done processes like that. And I think that's probably likely now. And it's taken many years of analyses of various meteorites to prove to really the whole community that you can form these igneous rocks like chondrules that we see. They're 80% of some meteorites, so they're everywhere. It had to be incredibly efficient. So you probably had to produce those by different types of mechanisms all over the solar system, including in the outer solar system. So I think I'm kind of leaning towards that way now, which is different than the conclusion I wrote in that paper. But we change our mind when we get there.
Yeah, that's the beauty of physics, right? Beauty of science in general. So we are sure that Jupiter has a rocky core. I saw some data, somewhat unrelated, Ryan. So this, the red spot, the famous red spot on Jupiter, it seems to extend thousands of miles into the planet, which is a mind-boggling thing to even think about. But the core itself, we are pretty sure it's rocky. And do we know how big that core is?
I think Juno, the mission Juno, will tell us more about that. And I have to confess I'm a little ignorant on their most recent results, so I should probably go look that up. But I think Juno, which is in orbit around Jupiter, will give us more of that information. And I'm unsure what the current state of the art is on that.
Yeah. So I want to go into a couple of your more recent papers. So one of them, Earth's water may have been inherited from materials similar to enstatic chondrite meteorites. You say the origin of Earth's water remains unknown. Enstatic chondrite EC meteorites have similar isotopic composition to terrestrial rocks and thus may be representative of the material that formed Earth. So this has been a puzzle. I mean, we got a lot of water on Earth. And so what's our latest hypothesis as to how that water came to Earth?
Right. Yeah. This is an ongoing debate in cosmochemistry, and this is kind of the last volley in that debate, which was a paper that was co-authored by my postdoc. And when he was here, we've worked on this type of problem on other samples, and we're also writing that paper right now. But so the most recent idea is that Earth is very similar to a particular group of meteorites called the enstatite chondrites. And it seems to be similar to those meteorites in various isotope systems, oxygen, and others. So it was thought that Earth possibly accreted enstatite chondrite-like material, and that ended up being the rocky part of Earth. But the problem with that was that Earth formed relatively close to the sun, and enstatite chondrites were thought to not have a lot of water in them. And this most recent study showed that perhaps enstatite chondrites have a bit more water than we thought. And the isotopic composition of that water might match the Earth's oceans. And if you believe these water contents in enstatite chondrites, which I don't totally believe yet, then that could be responsible for Earth's water. And this is a different idea. You may have heard previously, it's thought that Earth's water was delivered by asteroids, wet asteroids and comets. I think that's still a viable hypothesis. Part of the problem with that is with comets, they seem to have a hugely variable hydrogen to deuterium ratio. So we probably should match the isotopic composition of hydrogen and oxygen in the water that we deliver to Earth. So that's been part of the game, is matching the isotopic composition of the water from these various bodies to Earth's oceans, because that has to add up that way. I think that's probably still the more likely hypothesis. So my postdoc, who was a co-author on that paper, when he was here with me, we were looking to analyze with a new technique using the nanosims in our lab, the hydrogen and oxygen isotopic composition of samples from D-type asteroids. So we have a lot of samples from C-type asteroids. Those are the carbonaceous chondrites. We only have a couple samples from these D-type asteroids that are thought to form further out in the asteroid belt. So we developed techniques and were able to analyze material from these D-type asteroids. And with our analyses, we can possibly match, understand the contribution from the D-type asteroids to Earth's oceans as well.
So when you say isotopic composition, are you talking about sort of the deuterium to regular water ratio? What do you mean by the isotopic composition of water?
Yeah, so I'm usually talking about both oxygen and hydrogen isotopes. So hydrogen isotopes are deuterium to what we call hydrogen, normal hydrogen. And oxygen has 3 isotopes, oxygen 16, 17, and 18, 3 stable isotopes. So with hydrogen isotopes, it's actually very difficult because you can change the isotopic composition of hydrogen by simple processes like evaporation and condensation that can change that ratio pretty drastically. But when we look at the 3 isotopes of oxygen, the relative ratios of those don't necessarily change with those processes like evaporation and condensation if we look at a certain value called cap delta 17O, to use a very specific term. So we can look at that to really pin down the reservoirs, and that's why we use both of those.
Yeah, so that seems like a very interesting way to answer the question where it all came from, right? So if so EC was initially rejected because it didn't have a lot of water, but now we think it had water. Asteroids have been mentioned. Comets are generally all water, right? Typically, icy stuff.
Yeah, and that relates to what I said about it being very fragile. So when we do collect cometary dust in the stratosphere from converted Cold War spy planes, and we look at that dust, it's like all pore space. So what we think it is, I mean, the ice evaporates by the time we get it. So we get these particles that are very, very fluffy, like I said, and it could be that pore space is filled with ice. So the water to rock ratio on a comet could be 1-to-1, something like that. Dirty, you know, they said dirty snowballs. I might think of an icy dirt ball. Maybe that's a better.
Icy dirt ball. So that hypothesis is still at play, I guess, right? So all the water could have been delivered by comets.
I think so, yeah, because we see the deuterium to hydrogen ratio in comets, which we can measure spectroscopically from telescopes, varies by a factor of 100. But if you get the right mix, it might make the oceans.
And I mean, if these things were coming in, they would have gone to Mars, they would have gone to the moon. Why are we not finding? I mean, moon doesn't have sufficient mass to hold on to it, but why are we not finding water on Mars?
So it seems like we find evidence of lake beds and other things like that on historic Mars, and possibly evidence of condensing ice on Mars. It's hard to keep track because they have so much evidence of historic water on Mars that during the Amazonian period of Mars, for example, there's probably not as much water here on Earth, but much more water than there is now.
And so we have a lot of missions going on to Mars. So do you think we will get data from Mars that sort of settles this a little bit better? Because there's sort of pristine data that we could get, right?
Yeah, I think the thing I'm excited about for the Mars missions, I'm a sample person, so I like rocks in hand. And the problem with what I do is that I don't have any geologic context for my samples. Like, they're delivered from space, we find them on the ground, we don't know where they came from for the meteorites. For Mars, we're actually collecting samples now. We're getting drill cores and caching them, and we'll retrieve them via 2 other missions in the future. So I think we can do amazing stuff with rovers, but it's still another leap in capabilities when you actually have the samples in hand. So I think with the water question, I'm not sure. We have to collect the right sample. But with those samples coming back, it's not going to be for a while yet, but we'll be able to measure their detailed mineralogy at the atom level. And I think we'll be able to answer some of these interesting questions for sure.
I don't know if there's data, but do we have sort of sufficient understanding if you look at all the planets meaning Mars, Earth, Mercury, and sort of the rocky planets, their composition is similar? In other words, they could not have been formed by different processes, right? They could not have been bombarded by different materials, right?
Yeah, I think, we don't know. We can estimate the bulk composition of Mars, for example, from the meteorites that we have. Venus is less known. It's hidden from us by its thick atmosphere, and we've landed the Venera landers on Venus, the Russians did, but we don't know a whole lot about its surface. Mercury, we know from the Messenger mission, but we're just looking at the top crust, and this is part of the problem if we're talking about bulk compositions, I think the terrestrial planets all have relatively similar bulk compositions. If we're talking about that, to me, it's the terrestrial planets basically have one composition. The gas giants, Jupiter and Saturn, have another, and then the ice giants and the Kuiper belt are something else entirely. So we definitely see like a chemical fractionation with radial distance from the sun and the solar system.
Is there anything special about the solar system, Ryan? That so if we find sort of a extra solar system, could we assume that these types of processes are fairly normal? In other words, if it is in the in the Goldilocks zone, if there's a planet in the Goldilocks zone, it will get water delivered to it. It will hold on to that water, and it will have sort of an Earth-like characteristic. So is there something special about that vendor in the solar system?
Yeah, I think that's what we're. When my field started, in the 1800s, we didn't think about this, right? That we're studying the formation of our solar system as a type case for the formation of planetary systems in the galaxy. But really in the last 20 years and really in the last 10 years, we know that extrasolar planetary systems are not uncommon in the galaxy and the universe. So now we can see cosmochemistry and the formation, the first 5 million years of our solar system's history, as a type case for all of these other extrasolar planetary systems that we see. So, and ours is the most interesting because we know there's one planet capable and did host life, right? So it's the perfect case. And with cosmochemistry and with these meteorites, we can understand the formation of these events to within 10,000 years. We can do this very, very precisely. So I think, I don't know. We have the anthropic principle issue of like, we're here to ask that question. So maybe it's not fair to say that the solar system's typical. But if we really push on these cosmochemical analyses, we can know exactly how these things happened here. And that's why I'm interested in these problems that we've talked about already, like the building blocks of the solar system, the astrophysical context of the solar system's formation, and then the delivery of water to Earth, or how did Earth get that water? So those are the questions I'm interested in as a type case for how we can develop habitable planets elsewhere in the galaxy.
Yeah, there's also a hypothesis that life was delivered to Earth, right? Panspermia or whatever they call it. Do we have any evidence for that, or it's really difficult to find out one way or the other?
Yeah, I think that's hard. I think we find amino acids like in the comet samples that I talked about from Stardust. We definitely found amino acids there. My opinion is that empty space without an atmosphere and a magnetic field is a very, very harsh place to live. So I think the radiation environment's pretty rough, but if you're buried within a meter of the rock, you're shielded. I think the delivery of these primordial amino acids to Earth, that type of panspermia, I definitely think happened. In my opinion, I don't have a lot of expertise in this area. I think it's unlikely that life itself was brought here via asteroids, meteorites, cometary dust, that kind of thing. But I think the ingredients for it were. Because based on where we formed, we had to form close enough to the sun to be warm. But if we're too close, we can't have enough water. We can't have these organic compounds that form that we need to create life. So I think this idea of us not being an island, but having this exogenous material delivered to us so that life could develop is a really interesting thing. And that's why I think this paper that I sent you about the enstatite chondrites, it's really important. Like, how much of an island are we? And what did we need in terms of delivery from outside of Earth's orbital radius? Do we need to develop life on this planet?
Yeah, so if life is not delivered and life actually originated on Earth, then at least intuitively it feels like life becomes more rare. When we have an N of 1 experiment with even if you have the right raw materials, it's still an N of 1 experiment. Do you see it that way? If that's the case, the extraterrestrial life probability declines. elsewhere?
Yeah, this is a Drake equation problem, and yeah, I'm not sure. This is an extremely difficult question, and I always feel uncomfortable speculating on things I don't have data for. So the other thing that we just looked at was Earth's astrophysical environment, right? And what we saw is that the solar system's parent molecular cloud was likely irradiated by a nearby massive star, and this we think explains a lot of these isotope anomalies we see in meteorites. But if we look at other planetary systems that are irradiated by nearby stars, some of them don't survive, right? So some of them have these beautiful protoplanetary disks around them, which was an analog to the forming solar system. And they're being irradiated away by a nearby massive star. So by the time you could have formed planets, that disk has been photo-evaporated away. It's gone. So life couldn't form on that system. But we know in our solar system, it was kind of this Goldilocks environment, just like the question of the water, because we were close enough to a star to see the effects of it in terms of the isotope anomalies in the solar system. But if we were too close, we wouldn't be here to ask that question. So, and star formation happens in groups, in clusters. So when you have a smaller star like the sun, it's likely that you'll have large stars nearby. But if they're too close, we wouldn't survive. So I think there's a lot of these questions that go into like the Drake equation, like what are the chances of all these things? And this kind of astrophysical environment question is another factor of that Drake equation that, I think we're thinking more about now.
Yeah, so many things have to come together, but if the probability is still low, but you're multiplying it with a few trillion, things still happen elsewhere. The question is whether we'll ever find it. So you have another recent paper, you mentioned this, a cosmic symplectite recorded irradiation by nearby massive stars in the solar system's parent molecular cloud. So I was wondering, Ryan, so if Jupiter were a star, we would not have had a chance, right? It would have sort of destroyed the whole process, I would think.
Yeah, we would have been in a kind of binary system. Yeah, we see planets around binary type stars. I think just recently there was a report of a planetary system around a binary star, but I think it gets very complicated. This Goldilocks zone that you mentioned, I think it's much harder at that point. But yeah, I think if Jupiter had enough mass to ignite, then we probably wouldn't be here. That's right.
So you say in this paper, Sun's astrophysical birth environment affected the formation and composition of the solar system. Primitive meteoroids display mass-independent oxygen isotope anomalies that are likely caused by ultraviolet photochemistry of CO gas phase molecules. So what do we learn from this? Sort of the sun's effect on the solar system early on.
Yeah. So this is one of the, we're talking about the two biggest questions in cosmochemistry. Really, the water delivery to Earth is very important, and also this astrophysical context of the sun's formation. So what we saw about a little more than, say, 14 years ago now. So we don't know the detailed isotopic composition of the sun. Until we flew a NASA mission like that Stardust mission we talked about, a relatively inexpensive discovery class mission to collect samples of the solar wind so we can understand the sun's composition, isotopic and chemical composition, with that precision we need for our cosmochemistry analyses in the lab, which I said were extremely precise. So that mission flew to the sun, collected material, came back. They put the accelerometers in the return capsule upside down, so it crashed into the Utah mud, which was fine because we still got 99% of the science out of that mission. And the most important result of that was that the sun's oxygen isotopic composition was 6% lighter than everything else in the solar system. And 6% doesn't sound like a lot when we're talking about other things in astronomy, but in cosmochemistry, it's a huge, huge difference. And so this was the mystery that many of us have been trying to solve since those measurements were made at UCLA about 14 years ago. And so this paper that you mentioned is our take on this. And we didn't measure samples of the sun to understand this. We measured samples of this really interesting phase called cosmic symplectite, which seems to have that heavy complement to the sun's light composition. So the sun's light, the Earth's normal, we thought it was normal, and then this cosmic symplectite is heavy. And it seems to be the only thing in the solar system that has that heavy composition. And what I think of it as is the meteorites, a famous meteoriticist once said, the meteorites are tight-lipped witnesses to the beginning. So a lot of their record, a lot of their witness to the beginning got erased. But once in a while, something slips through, and that cosmic symplectite slipped through. It was discovered accidentally, and it's made of iron oxide and iron sulfide. And what we did was measure the sulfur isotope composition. And there are 4 isotopes of sulfur that we can measure. And with those 4 isotopes, I said with 2, it was hard. With 3, we learned more. With 4, we learned a huge amount. So with those 4 isotopes, we're able to constrain the ultraviolet spectrum of the star that caused this difference in isotopes between the sun and the rest of the solar system. And that spectrum did not look like the sun, but it looked like a massive star, an O or B type star that was nearby in the galaxy when the sun formed. So that one just came out, and I think it will change our field because I'm pretty confident that this was good evidence that our neighbors, and again, I'm interested in this idea that we're not an island, right? So Earth is not an island, the solar system's not an island, and it was profoundly affected by stars that are long since drifted away and exploded as supernova, or maybe black holes on the other side of the galaxy now. I don't know, it was 4.5 billion years ago, so a lot has happened. So that paper, I think, gave us that context. And it was a real testament to what meteorites can do, because we found this one little, or somebody else found it, we analyzed it, but this one tiny little phase in one meteorite that's like as big as my fist that somebody found in Algeria in the 1990s. And it's nowhere else. And we just got to find as many meteorites as we can, because there's another cosmic symplectite out there that recorded some other very important astrophysical process that we don't know about yet.
So this B-type massive star was in the neighborhood when sun was forming. That is the conclusion. Yeah. And so 4.67 billion years later, it's not there. So it would have burned out. It would have supernova a lot faster. I don't know the sizes of these things. So B-type star would have been gone very quickly, right?
That's right. 20 to 40 solar masses, maybe as small as 10, but many, many times bigger than the sun. So yeah, it burned out very quickly. Everything kind of drifts apart, and it's long gone.
And so, but it would have provided some material. So do we have, I mean, this is really difficult, but do we know the sort of the proximity distance to that when it existed?
We do, because it can't be too far away, else we wouldn't see the isotope anomalies that it created. And it can't be too close for too long, else we wouldn't be here to talk about it and have this podcast. So what I think, it was about 1/10 to 100th of a parsec away is what I'm guessing it was. And it would have looked, if we could see it now, that size star that close would be about as big as the full moon.
So when it burns out, it would have become a white dwarf or a neutron star or even a black hole. So do we know what what the ultimate fate of that thing was?
No, and if, it was so long ago, and we have, kilometers per second relative speeds compared to these other stars that form near us. So I did some calculations to think, like, is this a nearby black hole or nearby neutron star or what? But no, it would be just with the average relative speed between a couple stars, it would be, you know, a tenth or halfway across the galaxy. So it's in the field now. It's long. I like that idea of like, can we identify that neighbor, that ghost that almost destroyed the solar system? But it's there, but we'll never find it.
Yeah, I mean, there's some hypothesis. I know that this is not very popular one, that the planet 9 that people talk about is actually a black hole. And so I wondered if sun captured it after it burned itself out.
Yeah, this one would be massive enough that, yeah, it couldn't be. We would see something that large, that close. So this one is, you know, several solar masses, so it's long gone.
Yeah. So I know that there are multiple missions still, NASA missions thinking about these things. So if you were to conclude on this, Ryan, you know, so you look forward next 5-10 years, what are the areas that you are, you know, sort of most focused on, and what do you think we will, you know, will most likely make interesting discoveries in?
Yeah, I think we're bringing a lot of samples back from known bodies. And like I said before, we don't, like, I'm a physicist and I'm a rock person and I work with geologists. And if I can't give you the geologic context where that rock came from, I know a lot less about the science. And I can do a lot fewer interesting things. And it's amazing what we've done with the meteorites so far. But we're bringing samples back. The Japanese have already returned samples from a C-type asteroid. Theirs was called Ryugu. The NASA OSIRIS-REx mission is bringing back samples from asteroid Bennu. And these are going to be gram-sized samples, and we could do a lot. I could spend my entire career studying micrograms. So with grams, we can do a huge amount of analyses. So those two samples will be very exciting. In terms of more planetary type processes, the Chinese return samples from the moon. NASA will too in coming years. So, and I'm most excited about, and I hope this works out, but what we really need is a low velocity collection of cometary material. So I mentioned the Stardust samples earlier in this talk, and they were also compromised a little bit by how we collected them. So we collected them at 6 kilometers a second, and we may have lost some of that really fluffy stuff that I was talking about. So if we can go to a comet and go and collect it, grab a piece like we did with the asteroids, and bring it back to Earth, and I'd really like to bring the ice back too. So it's not, you know, we're sampling the rocks, but that rocks are half the story, and probably the ices are the more interesting story. So I'd love to have a cryogenic comet nucleus sample return. It's a priority of NASA for the New Frontiers, kind of their more expensive missions coming up in the next decade or two. I hope that works out, it gets funded, and I hope I'll still be around when the samples come back. These are long timescale things, right? And while we're waiting for these samples, we can analyze the meteorites and other things we already have. And I think that combined with, so astronomy, there are two very interesting things in astronomy that are happening now that weren't around a couple decades ago. Where astronomy is doing exoplanetary science, and those two things are the submillimeter observations of protoplanetary disks and exoplanet observations. So these two things, and they're using new satellites and new techniques and new observatories, but those two techniques are kind of like exoplanetary science, and that didn't exist. And now our community, we're rock people mostly, don't really talk so much with those astronomers. And I'm trying to do more of that. And I think integrating those types of observations of what's happening elsewhere with our very, very detailed, but very, very narrow view of what happened here can really inform our ideas of how you make planets and how you make planets like Earth, which is the most important planet after all. So I'm super excited about these connections with astronomy and these new samples coming back in the coming years.
Yeah, the good thing is some billionaires are interested in asteroid mining, as you know. Mm-hmm. So if NASA is collaborating with some of these people, so to bring a a piece of a comet, including the ice, that is a really interesting engineering problem, right? So I would imagine, so you grab something at 6 kilometers per second, you're going to lose most of it. So you have to, I don't know how you would do it. I mean, you cannot land on these things, right? You have to synchronize in so finely to make that happen. So there's a huge amount of engineering innovation that might.
Oh, yeah, and people are working on it of ideas to shoot something into a body, but you don't know the material properties of the body. And this is the hard thing, because the sample is what matters. So on these the remote sensing space missions where you're not bringing back a sample, you beam back the data to Earth, but a sample return mission isn't a success until you have that sample in a lab on Earth. So, I mean, I think I know, like, a cometary outside of a comet has been sitting in space and been irradiated and could be tougher than we think it is. So dealing with contingencies, like building something that could to go into a comet and grab material and bring it back and put it into a sample return capsule is incredibly difficult. But then dealing with contingencies, to me, I don't build these kind of things, and the people who do, I'm totally astonished by, because they have to make sure this thing works in a number of unknown parameter space, and it's amazing.
And then you have to put the accelerometers right side up.
I mean, it's amazing, and I always like to say that, but think of all the 10 billion things they did right. And this is space missions and space travel. Like, you could do 10 million things right and do one thing wrong, and it's catastrophic. Like, it is incredibly, incredibly difficult. So yeah, that mission, it crashed in the mud, and we had to change how we did the analyses, but it took longer, but we got all the science out. It was really incredible.
Yeah, I mean, the other thing that's happening, obviously, there is a lot of development in artificial intelligence, robotics. So human tends to be sort of the weak link in the process. So if you take the human out, I think you reduce errors in the process as well.
Yeah, imperial metric conversions, and there's been lots of things like this. And when I think about that, I think how many mistakes I would make if I was building one of these things myself. So yeah, it's not easy, but we've done incredible things, and I think doing small missions, I think, is the future too. So like the complexity, as anybody knows that's written code knows, the longer it gets, it gets twice as long, it doesn't get twice as buggy, it gets 4 times as buggy. And I think this happens with space missions that get exponentially more complicated. And I like these ideas of simple, clever, focused missions that do just one thing very well. So I hope we do more of that kind of stuff.
Yeah, I mean, it also has sort of spillover benefits, right? A lot of people are worried about a meteor hit. And I'm not sure if we have sufficient defenses against that. So whatever we do in this space gives us knowledge and experience in that direction. The other thing I was wondering about, Ryan, couldn't our technologies improve? Couldn't we get, sort of spectral analysis in more refined fashion? Do we have to really get a sample? Couldn't we figure this out from a distance?
Yeah, there's a lot we can do from a distance, and we can measure isotopes with vibrational spectroscopy. So we got a diatomic molecule, and if this atom's heavier, it vibrates at a different frequency. So we're able to measure isotope ratios astronomically, but we can't do it with very high precision. So that's why if I have the sample and I polish it and it's flat and I fire a beam of cesium atoms and ions come off and I accelerate them and I count them one by one in the lab. And that is as good as you can get. So if we're looking at, big changes in isotope ratios, astronomical spectroscopic measurements are fine. But just to compare what we know about the first 5 million years of the solar system's history, a lot of it comes from isotope measurements. We're able to measure the solar system's age, a 4.5 billion year old thing, to within a few tens of thousands of years. And that's the type of precision we can do with laboratory measurements. And it's getting better. Like, the instruments that you can fly on a spacecraft are getting better, and we can fly more advanced things, but the laboratory measurements are also getting better because those are driven by other industries, right? They're driven by semiconductor industries where there's a huge amount of money going into developing these things. And then I use these techniques to look at comet rocks. And I'm just piggybacking off of these enormous laboratory technical advancements, which are happening very rapidly too. And I say, oh, that's a cool thing. Can I put a piece of comet dust in that instrument too?
Yeah, that's interesting. So both the fields are developing together. Perhaps the laboratory measurements are developing faster because of other industries really doing a lot of R&D in there. And so it seems to me that, Ryan, your need to hold the rock in your hand could be dominant for a long period of time, even if our observational capabilities improve a lot.
Yeah, and and I think they're going to work in tandem. And it's amazing what we can piggyback off of. Like if we just, I saw somebody argue that we can do an amazing amount of really cool astronomy, flying a small spacecraft by a bunch of comets and asteroids and taking pictures of their nucleus just with an iPhone camera. Like the light gathering ability, it's not radiation hardened, and that's a slight complication, but we don't need to develop these cameras because it's already just literally take it out of the iPhone and put it on a small spacecraft and it could do amazing things. So it's great to piggyback off of all this R&D that other people have done, that's for sure.
Excellent. Yeah, this has been great, Ryan. Thanks so much for spending time with me.
Great. Thank you. It's been fun.
Thank you.